So welcome everybody to this week's Oxford Discrete Maths and Probability seminar, and we're going to kick off with Cécile, who's going to speak to us about the ants walk, finding geodesics and graphs using reinforcement learning. It's lovely to have you here, Cécile.
Thanks a lot. Thanks a lot to you, Christina, and to Alex for the very nice invitation. It's a pleasure to talk to you about this project, which is a collaboration with Daniel Kious, who is here in the audience, and with Bruno Schapira. Daniel is based in the University of Bath, just as myself, and Bruno is from the University of Marseille. And in this project, our idea was to introduce the probabilistic model for a phenomenon that has been studied quite a lot in math biology, and also using mean field models. And in particular, we discovered this problem by reading a book which is called Ant Colony Optimization of Dorigo and Stützle. And in this book, they look at different problems that ant colonies are capable to optimize using almost no means of communications except the pheromones they lay behind them. And in particular, in our project, we were interested in this phenomenon, which is that ants are capable to find the shortest path between their nest and a source of food, just using these pheromones they lay behind them. So this is a phenomenon that has also been studied using mean field methods. And in particular, there is a researcher at the University of Uppsala called Sumter, who has a series of papers about this. But as I said, our idea was to define a probabilistic model for this and to study it. So let me describe to you the model we introduced. And in this model, the environment in which the ants live is just a graph, a finite graph. So it's fixed, it's finite, and it's called G with set of vertices V and set of edges E. And in this graph, we have distinguished two nodes, which are the node N for the nest and the node F for the food. So N is the nest and F is the source of food. And the ants are going to walk on this graph. They're going to perform successive random walks. I'm going to tell you their distribution, but the aim is for them to eventually go from the nest to the source of food following the shortest possible path in the graph. And just to tell you, every time I'm talking about distance in this talk, I mean the graph distance. So each edge has length 1. So how do we define the model? Well, this model is going to be, in fact, a model in which the graph, the edges in the graph have weights. And at time 0, all edges have weight 1. And then these weights are going to evolve. I'm going to tell you how. But if you want to keep in mind, the weights are going to represent the amount of pheromones that are deposited on each edge. We start at 1 just because otherwise it's a bit strange. But so what happens next is that we're going to throw the ants one by one. So, and each of them is going to perform a random walk starting at N and stopped when first reaching F. Okay. So each ant performs a random walk from N, starting from N, and stopped when first reaching F. And the transition of the random walk are proportional to the weights. So what do I mean by that? I'm going to give you here a little example. So let's say the ant sits at a node here, the blue node, and it has the choice to hop to one of these 3 edges. Then the transition, let's say the 3 edges have weight 1, 3, and 2. Then with probability proportional to 1, the ant is going to hop to this vertex. And here, therefore, it's with probability 1, 6, because the total sum of all 3 weights is 6. With probability a half is going to jump to this vertex, and with probability a third is going to jump to this vertex. And it does that every time it hops across an edge. And now I need to tell you, how do I update the weights? So every time an ant reaches F, I just stop and I update the weights, and then the next ant starts from N and performs a random walk. So when the ant reaches F, we update the weights. And what we do is we're going to do +1 to a subset of the trace of the ant. So what's the trace? The trace is all the edges that have been crossed at least once by this ant. And I'm going to do +1 to some of them. And I'm going to tell you which of them in the next slide. But the idea is really that this +1 represents the pheromones, right? So I've left an amount +1 of pheromones on these edges. Before telling you how I do that, I just want to insist on the fact that in this model, it's really we are really looking at some linear reinforcement. Why? Because if you look at here at the weights, so the weights are proportional to the number of ants that have deposited pheromones on them in the past. And the ant that is walking on the graph at some time n reacts linearly to these weights. So it's really linear reinforcement, as opposed to sublinear or superlinear that also exist in the literature. So let me tell you what subset of the trace do I reinforce at each time step, after each ant has reached the food. And in fact, there are 3 ways to do that. So it means that we don't study one model, we in fact study 3 models. And in fact, this is done in 2 different papers, but I'm going to tell you how it's separated in the papers. The first model is the most natural one. I'm going to call it T for trace reinforced. In this model, I'm going to do +1 to all the edges in the trace. So +1 to all edges in the trace. So for example, let's say my ant number n has done the following trajectory, like this, like this, like this, like this. Here I just do +1 to all edges in the trace. So here this edge is in the trace, this edge is in the trace, they're all in the trace in fact, except this one here. And I just do +1 to all these green edges, right? And then I start the following random walk and I do that and so on and so forth. If you want, this model means that the ant leaves the pheromone on its way forward to the food, right? So it's walking to the food and it deposits some pheromones, and then it stops at the food and stays there forever, and the other ants then start walking again. The other 2 models that I'm going to define now, you have to imagine that this time the ant is going to deposit the pheromone on the way backwards from the food. So if you want, the ant gets excited once it's at the food, and when it's excited, it starts depositing pheromones. And the question is, which way does it choose to come back to the nest? And we're going to assume that the ant is a little bit smart and tries to come back in an effective way. And we're going to introduce 2 models for that. The model LE for loop erased, because here the ant is going to do some loop erasing version of its trajectory, but taken backwards in time. So if you know what a loop erased random walk is, you have to imagine that the ant is going to follow its trajectory backwards in time and erase the loops. But if you don't know what it is, I'm going to tell you another definition, which is completely equivalent. So let's say, for example, that the ant has done this trajectory. And then I follow my trajectory backwards. But when I have the choice between several edges, so here I could choose this one, or this one, but I choose the one that I've crossed the earliest on the way forward to the food, right? So here the first time I came to that node, I was coming from here, therefore I'm going to reinforce, I'm going to come back this way. No, I made a mistake, sorry. Look, So the first time I came here, I came through here, so I reinforce that edge here. Then here I have no choice, I came from the left, and here again I have the choice between this edge and this edge, but again I was coming from, the first time I came, I was coming from this one. So you take the earliest, if you have a choice, you take the edge that you crossed the earliest on the way forward. And you do +1 to all the edges in green. The third model is one which we call geodesic reinforced, so geodesic, because this time, so again, so the ant has followed some trajectory. I take the same example in 3 definitions. And this time we have to imagine that the ant has a partial map of the graph. So it's explored a subgraph of the big graph. And in this subgraph, there are some shortest paths to go from the foot back from the foot to the nest. And the ant is going to take one of these shortest paths. These don't have to be shortest paths in the complete the graph G, but they are shortest paths in the partial map that the ant has explored, in the trace of the ant. So here you can see that there are 2 shortest paths. There is here a path of length 3, but also through the right, there is here a path of length 3. And so I chose this example to show you what happens when I have ties. Well, I just flip a coin, right? So I choose one of these uniformly at random. So I'm going to do here +1 to the green one with probability 1/2, or I'm going to do +1 with probability 1/2 to the right. Okay, so just to tell you a bit about the math biology literature, in fact, both model T and LE are considered in the biology literature. As far as I know, I don't think the G is studied, but it seems quite natural from a math point of view. And unfortunately, this model, which maybe seems the most natural from a math point of view, is the hardest to study. Did I forget? I forgot to, sorry, here I realized I forgot to put this one as well. So this one is the hardest to study. So in fact, with Daniel and Bruno, we submitted a paper on the archive in September and October in which we treat these 2 cases. And we are hoping to submit a paper about the trace reinforced in the following days. I can see someone raise their hands. Christina, yeah.
I have one quick question. Is an ant allowed to backtrack? If I go on an edge, is an ant allowed to go back on that edge, or does it exclude that from its choices? Yeah,
that's perfectly fine. I'm allowing backtracking.
Okay.
Yeah. Thank you. Right, I hope the models are clear. If yes, I can go and tell you. Yes.
Actually, I actually have one other question. If you could go back up.
Yeah.
To the one on the far left, the trace reinforced. If an ant takes an edge multiple times, is it going to get reinforced multiple times?
No, very good question. No, I just do +1.
Okay.
Yeah, thank you.
Cécile, perhaps while we're here, I can pick up a question that's come up in the chat.
Yeah.
From Alexander Turinen. He says,
I'm happy to ask that in words if people don't mind. So in these models, essentially the reinforcement you have, I presume later will be used to sort of help the ants learn. So what I'm wondering is, are you considering essentially the case where the rule by which the ants learn how to find a better path is something that's kind of posited as an assumption, and you study the properties rather than kind of thinking about a higher level principle, like for instance, an optimistic principle that's common in bandits and reinforcement learning, and then studying what sorts of like actual learning rules arise from that?
No, yeah, so I'm defining the model, and then I want to look at whether under these different models, I find the shortest path or not.
I see. Okay, thank you very much.
Thank you for asking. Great. Very good. So let me tell you about our results and our conjectures. So maybe there are more conjectures than results, but that's exciting. To state these conjectures and results, I just need one notation, which is the following. So I'm going to denote by WE of n the weight of edge E. at time n. So at time n means after the nth aunt, but after I have updated the weights according to the trajectory of the nth aunt and just before the n+1th aunt starts walking. And in fact, so with this definition, we have that WE of 0 is 1 because at time 0, I said that all the weights are equal to 1. So for all E in my set of edges. So let me define a little bit some element of languages with some mathematical definition. So I'm going to say that the aunt process converges if there exists a sequence chi-e indexed by the edges. These could be random variables, right? They could be deterministic, but I'm allowing them to be a random variable such that almost surely the weight of the edge E divided by n converges by almost surely as n. Well, I've already said almost surely. Oops. I've already said almost surely, but converges almost surely to chi-e. Right, so I have some kind of convergence, right? I converge to something. And we say that the aunts find a shortest path if, in addition, so I'm asking that the process converges, and in addition, almost surely, chi-e is not equal to 0 implies that E is on a geodesic from N to F. So this just means that the only edges that have a non-zero weight are geodesics that lie on are edges that lie on a geodesic. So it means that eventually almost all aunts are going to go from N to F following a shortest path. So they found the optimum solution. So let me tell you what we proved. So I'm going to start with the results from the first paper. The first theorem is as follows. So in model loop erased, so LE, if G is a series parallel graph, and I'm going to tell you just after what it is, then the aunts find shortest path, a shortest path. Okay. So here I'm going to write the definition of series parallel graph, but you're going to see that these graphs were probably originally defined in electricity, as you can guess from the name, and they are very natural in our context because there are graphs in which two nodes are distinguished. One of them is called the source and the other one is called the sink, and it's very natural for us to see the source as the nest and the sink as the source of fluid. And in fact, I'm quite pleased Ben Hambley is in the audience because there is a famous probability paper by Ben and Jonathan Jordan in which they look at the resistance, I think, of some a model of random series parallel graphs. So they also appear in the probability literature. But let me tell you what it is if you don't know. So a graph, I'm going to give you the recursive definition. A graph G is a series parallel graph if, well, there are three cases. The first one is the base case, which is just an edge between N and F. So this is G. Or it is two series parallel graphs, G1 and G2, plugged in series. So here you see, I'm going to put some, so this is just, you take one series parallel graph, another one, and you merge the source of fluid of the top one with the nest of the bottom one, and you obtain a bigger series parallel graph. And the third option, of course, you have guessed, is to merge two series parallel graphs, but this time in parallel, like this. So G1 on the left, G2 on the right. So this is a recursive definition. So here I have merged the two nests together and the two sources of fluid together. And this is the definition of a series parallel graph.
Cécile, could I just ask about your definition of finding a shortest path?
Yes.
Because you could have a subgraph where every edge lies on a shortest path in the whole graph, but it doesn't actually contain a shortest path from N to F. So is it that there's actually a shortest path in the graph that they find, or
no? So yeah, so in fact, so on purpose I was trying to no. So what we would have liked, in fact, is that if there are several shortest paths, they find them all, in the sense that a positive proportion goes. So if you had only shortest paths, we would like that the ants just go a bit everywhere. But in fact, so yes, but we're just happy if they find one. Does it make sense? It doesn't really matter what happens in your case, I want to say. But
okay, but you could have a graph where every edge lies on a geodesic from N to F.
Yeah, and then
yet they end up finding a path that they end up exclusively going down a path that is not a shortest path.
It could, that is not a shortest path, no. Sorry.
So every edge lies on some geodesic, but the whole geodesic doesn't occur inside the subgraph that they find. So for instance, if you go from the top of a cube to the bottom between two opposite vertices of a cube, you can find, so every vertex lies on a geodesic there. So every edge rather lies on a geodesic.
Yeah.
But if you put N and F at two opposite corners, you can find some kind of long wiggly path that isn't a geodesic.
This could be that you're right, yes. So what I said was wrong was to say, okay, so you're saying what I said when I said all the ants are going to go from N to F following the shortest path could be a bit wrong in that case. That's, thank you.
Okay, thank you.
Thanks a lot. What I said was wrong, but the theorem, so what we believe is that this is true, and the second statement I said is probably wrong, you're right. Thanks for asking.
Okay, thank you. Sorry to interrupt.
Thank you. No. Thanks a lot. I didn't think about that, so thanks. Great. Okay, so for the series parallel graphs in the LE model, we find the shortest path. And then, of course, so we believe this is also true in the geodesic model, but we haven't done the proof because we believe it's harder. But after writing this proof, we wondered, what about non-series parallel graph? And so to start with, we decided to look at the simplest graph that is not series parallel that we could think of. And this is the graph we call the losange, which I drew here. So a five-edge graph with a little bridge here. And in fact, the second theorem of our first paper says that on the losange, in model G, geodesic this time, the ants find the shortest path. Find a shortest path. So this just means here, there are two shortest paths, one the path to the left and the path to the right. So in fact, what we proved is that the weight of the edge in the middle goes to 0. And I've numbered the edges from 1 to 5 to tell you exactly what we proved. In fact, we proved that the weight of edge number 3 goes to 0 almost surely when n goes to infinity. But we also proved that the chi I is not 0 almost surely for all I not equal to 3. So in fact, the weights, so a positive proportion of the ants are going to go through the left path and a positive proportion of the ants are going to go through the right path. And here you could be a bit disappointed in us because with the first theorem treats a huge class of graphs, right? All series parallel graphs. And the second theorem is just about this 5-edge little particular example. But in fact, go and see our paper because the proof for the losange is longer than the proof for the series parallel graph. And it's harder, arguably. So this is bad news because it means that maybe we don't really know how to treat other graphs, right? So other graphs that are not series parallel and that are not the losange. That said, we do have a conjecture, and the conjecture is that in models G and LE, ants always find shortest path. But we're not able to prove that. But that's it. So that's basically the results of our first paper, which you can find on the archive. And now I want to tell you what about model T, right? Which is maybe the most natural one. And here things become complicated. So let me tell you why they become complicated. They become complicated, spoiler alert, because the ants don't always find the shortest path in that model. That said, we are able to prove that sometimes they do find the shortest path. So the first theorem of the second paper, which is Theorem 3, is that in model T, if G is tree-like, I'm going to tell you what tree-like is in a second, and if the distance, the graph distance, right, between N and F is 1, so N and F are just very close, right, just one edge between them, then the ants find the shortest path, or find shortest path. Okay, so what's a tree-like graph? So a tree-like graph is a graph that is rooted at N. And so, sorry, it's a tree that is rooted at N. And I've taken all the leaves of the tree and I've merged them as one node. So here I'm not adding edges between them, I'm really merging them into one node. And this one node is the source of food. And so here you see it's really, this example here is really in the framework of the theorem because I am tree-like and I have one edge between N and F. And so in that example, eventually all the ants, almost all the ants go from N to F through this one edge. Okay, but this is when the bad news come. We were not able to find, I think, any other example for which the ants find the shortest path in this model. So the theorem is that in model T, in the following graphs, the ant process converges to some limit chi e, where, and I'm going to tell you, so I've put chi e in green because basically to state the theorem, I'm going to draw you the graphs. So they're already drawn here, and I'm going to write in green the weights, the limiting weights of all of the edges, and we're going to see that indeed the ants don't find shortest path. So the first example is, so we were wondering, okay, basically we started from this theorem and we were like, okay, what if I have a graph that is tree-like, but in which the distance between N and F is more than 1? And so the first example we looked at was just to have two paths, one path to the left of length P, and we take PQ more than 2. So a path of length at least 2 to the left, and a path of length at least 2 to the right. There could be both 2, there could be 2 and 3, etc. And in that model, the limiting weights are some alpha squared, etc., alpha to the P on the left branch, beta squared, beta to the Q on the right branch, where so alpha and beta are non-zero, and their solution, they are the unique solution of alpha P to the beta Q equals 1. So we know exactly what the limiting weights are. And of course, the ants don't find the shortest path because, for example, if you take Q larger than P, you still have a positive proportion of the ants going through the right branch. Great. The second example, we decided to look at it because we wondered, okay, so what if in this theorem, I keep the distance between n and f being equal to 1, but I remove the tree-like, you know, what happens? And of course, we decided to remove the tree-like, but to go from tree to series parallel, right? Because this is series parallel is a bit less than asking tree-like, but yeah, it's the next step somehow of generalization. So we looked at this graph, which we call the cone, because you can see it looks a bit like a cone if you imagine it in 3 dimensions. Between us, we call it the ice cream cone, but the cone is fine. So, and in this graph, the limiting weights are the following. So we do get 1 here and 0 there, but bad news, we get 1/3 on the double edge. So this means that indeed, almost all the edges are going to end up going to the source of fruit through this edge, but some of them are going to lose some time somehow, you know, it's not the most efficient, so they lose some time here. So in the end, we don't find the optimal solution. So that's bad news. And then the third example we looked at was the losange. So here our motivation was really because we looked at it in the previous paper. So we wondered, you know, how does the model T behave on this example? And we are able to prove that here the limiting weights are 1/2, 1/2, 1/2. And here some W star, where W star is the unique solution of this equation. So I'm just writing it to show you we have it, but really it's not very important. Minus 3/2 equals 0 on 0, 1. So W star is not 0, it's not 1. Okay, so here again, we don't find the shortest path because we still have a positive weight on the edge in the middle. But all these examples somehow are interesting because you can see that I've told you when I introduced the chi-e's that the chi-e's could be random, but in fact here they are always deterministic on these examples. And in fact, it's a belief we have that for all graphs, as long as you don't have a double edge near the fruit, then the limiting weights are going to be deterministic, but we're not able to prove it. That's it for all the results. It's a good time for questions if there are questions. Otherwise, I'm going to tell you a little bit about other papers and ants, and I'm going to tell you then about the methods of proof. So other papers on ants. So I've cheated, I've kept them written on my paper here. So maybe you've seen this paper, which is very recent on the archive, and it's called the Ant Mill. So it's written by Erhard, Franco, and Rice. And I think their model is a bit related to a model of Le Goff and Raymond from 2018. And in both these papers, they are inspired by ants as well, and they also look at, you know, ants lying pheromones behind them. But I think the main difference between their models and ours are that first they use superlinear reinforcement and not linear reinforcement like us. And also it's only one ant, so it's some kind of self-reinforcement, whereas with us we have a sequence of ants. So this is a bit different. And in fact, their result is a bit different as well. So I think in both papers, the ants end up being stuck on a random cycle. So the ant basically forever cycles on this cycle, if I'm not wrong. Our model is also related to other probability papers, which are not about ants, but there is this paper of Benaim, Benyamini, Chanel, Lima from 2015. So this is about Pólya urns with graph-based interactions. And they look at both superlinear reinforcement, but also linear reinforcement in some cases. But it's a bit different because they always only reinforce one edge, whereas we reinforce more than one edge. So the model is a bit different. And I also wanted to mention this paper of Van der Hofstadt, Holmes, Kuznetsov, and Russell from 2016. And this model is basically a generalization of the paper of Benaim, Benjamin, Chen, and Lima. And it's the same, they always reinforce only one edge, and it's super linear reinforcement. So I would say the specificity really of our paper, I mean, of course, the models are all different, but what's maybe interesting is that we look at linear reinforcement, and this is enough in some cases to find an optimal solution. Okay, methods of proofs, and I'm going to show you on some examples why these methods might be useful, hopefully. So we use 3 methods. The first is using couplings with Pólya urns. The second one is just a tool to calculate probabilities of random walks on a weighted graphs. So it's the method of electric conductances, which, for example, is explained in a book by Lola and Limit. And thirdly, we use stochastic approximation. And in our first paper, so about the geodesic and the loop erased model, I would say that we really use the three methods, and in particular Pólya urns and stochastic approximation, a mixture of both. Whereas in the second paper on model T, we really only exclusively use the Ode method, so which is a stochastic approximation method. And for example, we applied results from Benaim or from Pimentel, from the survey of Pimentel. So as I said, I'd like us to look together at some very simple examples of graph and see why should it be that the ants find or don't find the shortest path. And hopefully it's going to give you an idea of the proofs. The first model I want to look at, there is really no shortest path to find, but let's see how the ants process behave on this. It's the following graph. So I just have the nest and the food, and I just have 2 edges in parallel between them. Where do the ants go? You know, what's the limiting weights on that graph? In fact, you can check that the 3 models, so L, E, G, and T, they all behave the same on that graph. They make no difference because you either do +1 to this edge or you do +1 to the edge. The ant only does 1 step. I mean, it's very simple. So they're all completely similar. To study it, the calculation we're doing is the following. We're asking, what's the probability that, so I'm numbering my edges 1 and 2 for convenience. So what's the probability that the weight of the first edge is going to be increased by 1 at time n+1? So knowing everything, knowing the weights at time n. So this is just asking what's the probability that the ant number n+1 is going to go through edge number 1. So this is very easy, right? So this is just by definition of the model, the ant goes through edge number 1 with probability proportional to the weight of that edge, right? So basically with probability W1 of n divided by W1 of n plus W2 of n. So here we stop because we recognize the formula that appears when we look at Pólya urns. So the classical Pólya urn that we teach in undergraduate here is the following. You have an urn, and in this urn you have balls of 2 colors. You have, say, green balls and pink balls. We're going to imagine in our heads for a moment that W1 of n is the number of pink balls in the urn at time n, and W2 of n is the number of green balls in the urn at time n. Then this formula says the following. It says the law of this urn is I pick a ball uniformly at random, and if it's green, I add a green ball in the urn. If it's pink, I add a pink ball to the urn. So we know, I mean, this is very classical, right? You can calculate almost everything. There is a martingale. It's an exercise to prove that W1 of n, in that case, divided by n, the proportion of pink balls converges almost surely to a uniform 0, 1 when n goes to infinity. So the limiting weights, the chi is a uniform here and 1 minus a uniform on the right-hand side. Okay. This was a warm-up. Let's have a look at a case that is tiny bit more complicated, and at least there is a shortest path to find. So here I have 3 edges. This one here, which is between n and f, and then I have a path of length 2 between N and F. Again, the calculation starts the same. I want to calculate what's the probability that the weight of edge 1 increases by 1 at time n plus 1, knowing everything up to time n. And this time, maybe it's a bit harder to calculate. I'm going to show you how the conductances method works. And to do that, I'm going to open my graph here, and I'm going to separate F into 2 points, F1 and F2. So this is edge 1, and this is edge 2, and this is just N. So you see here, no, sorry, this is edge 3, this is edge 2. So you see I've just opened my graph like this. And now basically what I want is the probability starting from N that I'm going to reach F1 before reaching F2, right? Because this is exactly the probability that I reinforce edge number 1. Just one little caveat here. The calculation I'm going to make here, well, no, that's fine. No, that's fine. I'm saying that later. So the probability that starting from N, I reach F1 before reaching F2. In the books of Lola and Limich, they tell you this is the effective conductance between N and F1 divided by the effective conductance between N and F1 plus the effective conductance between N and F2. Let me tell you what these are. It's very simple. If the effective conductance between N and F1, so since it's just an edge, it's just its weight. So in fact, this is just the weight of edge 1. Now for the effective conductance between N and F2, here you just have to remember the formulas you learned in electricity at school, really. So at school you learned that to get the conductance of 2 edges in series, what you need to do is 1 over the effective conductance of the first one plus 1 over the effective conductance of the second one. Okay, so here it's not a super nice formula, but we're going to remember, and this is where I'm going to make a distinction between the models. In model G and LE, we have that Wn is equal, W2 of n is equal to W3 of n for all n. This is because in these two models, the ant is either going to do +1 to edge 1, or it's going to do +1 to edge 2 and edge 3. So these weights are always equal. So this is really nice because it means that in this case, in these two cases, this conductance becomes W2 of n over 2. So in total, I get for this calculation, I get W1 of n divided by W1 of n plus W2 of n half. And this half is very important. And in fact, let me tell you, so I like Pólya urns, and so to me, it's very clear when I think about the Pólya urn. So it's the same again, except that this time, the pink balls, you have to imagine that they are much bigger. So they are twice as big as the green balls. So this is intuitively, but what it means is that each pink ball is twice more likely to be picked when I pick a ball than a green ball, right? And it's shown in this case, I mean, you can just do, again, it's a bit of an exercise. You can show that in this case, this gives a big advantage to the pink balls. And in fact, their proportion converges almost surely to 1 as n tends to infinity. So this is really good because it means that in the geodesic and the localized model, the weight of edge number 1 goes to 1. This, of course, implies that the weight of edge number 3 goes to 0. And in fact, since the weight of edge 2 is equal to edge 3, this goes to 0 as well. So we do find the shortest path. And why I like this idea, this image as an urn is the following, is that in reinforcement learning, you're supposed to give a reward to successful trials. And here you could be, Cécile, from the beginning, you give rewards every time. Whatever the ants do, you give a reward +1 to its trace. But here you can see that, yes, but I give a bigger reward, so a bigger ball, a big pink ball, when I give a reward to a short path, and I give a small reward when I give a reward to a longer path. And this is what makes us find the shortest path eventually. Okay, so what about model T and all that? So I haven't told you what happens in model T. So let's have a look in model T. In model T, I don't have this equality, but I have the following. I have that W3 of n is always smaller than WT2 of n, because if I reinforce H3, I must reinforce H2 as well, because the only way to have crossed H3 is to have crossed H2, right? And this means that, okay, I don't have an equality. So this is not an equality, but this is a less or equal. And this means that here I have a more or equal. So in fact, I can say that, so here I have a more or equal, and I can say that the weight of my F edge number 1 dominates the number of pink balls in the urn I described to you before. So it's even bigger. It's even bigger than something that goes to 1, and it can't be more than 1. Right? So in the model T, we still get that W1 of n renormalized by n goes to 1, but this doesn't imply straight away that the weight of H2 goes to 0. Right? So this implies that the weight of H3 goes to 0, but what about the weight of H2? So I want to tell you very quickly about how can we prove in model T that the weight of H2 goes to 0. So in model T, I need to show that the weight of H2 goes to 0 almost surely. So again, it's always the same calculation. I'm looking at what's the probability that I reinforce edge number 2. And it's equal to the probability that I'm going to reach this point here, starting from n, before reaching F1, right? Reaching this point, starting from n, before reaching F1. So again, it's just W2 of n divided by W1 of n plus W2 of n. Here I'm going to do a little trick. I'm going to define W hat I of n as being the weight of edge number I divided by n. And you can see I can just put hats everywhere, right? Because I just divide the top and bottom by n. And here, what we have shown before is that this here is approximately 1. And here I'm going to be a bit hand-wavy, but the whole idea of our proofs is to make this kind of argument rigorous. But basically, this means that this is approximately W hat 2 of n divided by 1 plus W hat 2 of n. And this means that W hat 2 of n is a stochastic approximation, which means I can write it satisfies a recursion of the form W2 of n plus 1 is equal to W2 of n plus 1 over n plus 2 times a function of W hat 2 of n plus a martingale increment. This is a stochastic approximation. And here, f is just this function minus the identity. So f of x is just x over 1 plus x minus the identity. And this is just minus x squared over 1 plus x. And this is where, on this little toy example, I can tell you what is the Ode method, but this is a very simple example. The Ode method tells you that W hat 2 of n follows the flow of the ODE y dot equals f of y. And here you can see, here this function f is always negative. So in fact, and W hat lives between 0 and 1. So if it follows the flow, it's only going to get pushed to 0. And in fact, this is how you can prove that, therefore, since f is negative, then on 0, 1, then W2 hat of n converges to 0 almost surely as claimed. So this is just a little glimpse to tell you I think on this little example, you can really see what's going on, right? Why is it that this algorithm does output the shortest path? And why is it that the model T is more complicated, right? Why is it that it's more complicated? And we can really see why on this little example, and we can see why the Ode method is going to be useful. I think I've got 3 minutes. So 3 minutes to tell you how the proofs work for the big theorem I announced at the beginning. So I'm going to be very quick. So ideas of proofs. The first is, how do we do the proof on series parallel graphs for model LE? Well, the definition of the series parallel graph is a definition by induction, right? It's a recursive definition. So of course we do the proof by induction, right? That's what I will say. So proof by induction. The second, for the losange. So for the losange, we really do a little bit of coupling, I mean, a lot of coupling with Pólya urns and a very fine analysis of some Pólya urns, and also some stochastic approximation. But again, it's very ad hoc. It really depends on the explicit formulas we can calculate for the losange. And that's why we're not very optimistic about generalizing to other graphs. And 3, I want to tell you a bit more about model T. So the paper that is supposed to come soon on the archive. So for model P, we really do some stochastic approximation. So for model T, what we do is we introduce again, so W hat of n is just the vector of the weights we normalized. And basically we show that this is a stochastic approximation. It's very easy. So we show that W, I plan to do it, but since I'm running late, I'm not doing it. But basically you can show very quickly that as a vector, so I want to remove E, as a vector, W hat is a stochastic approximation. And here you get some function plus a martingale. The martingale increment is really nice because it's bounded. So the martingale is very nice. And what we can prove is that, in fact, for any graph G, probably connected, I guess, if I'm not, but basically for any reasonable graph G, F is Lipschitz, which is one of the good conditions in stochastic approximation theory. It's nice to have F Lipschitz. And we can prove that this is true. And to analyze the graphs, all these examples I gave you, we basically need to analyze the ODE. So we need to analyze the ODE y dot equals f of y. But as you can see here, it's much more complicated than the little example I showed you before, because f is the dimension, I mean, is the dimension of f, okay, f takes a lot, the dimension of W hat as a vector is the number of edges in your graph. So this is just huge, and you need to understand this ODE, and it's not linear at all. And this is what's hard to do. There are lots of other open problems, right? So you've seen that we've made a few conjectures that we would like to solve eventually. In the book of Dorigo and Stutzler, there are lots of other optimization problems that ants can solve. For example, the traveling salesman. And maybe you've heard as well as about a slime mold that also can use reinforcement learning to find some optimal transport problems. So I think we have enough research material for the next 20 years. Thanks very much for listening.
Cécile, thank you for a beautiful talk. That was super stimulating. Can I invite any more questions from members of the audience? I know that Alex has one, so maybe I'll let him kick off.
Okay, yeah, thank you for a delightful talk. I had a couple of questions. One, you had these sort of very nice conjectures. Have you done some simulations to see if they seem to be true?
No, so the simulations, I have to say, so, okay, so I think none of us is qualified for doing very good simulations. I have tried a little bit, and it's just very slow. So unfortunately, this is often the case with these models of linear reinforcement. But yeah, so it's too slow to see anything. So even on the models for which we know it converges, it's just too slow to see anything.
Okay, thank you. And then the other question I had is, so kind of thinking just about ants, it would be quite natural to think of actually living on the kind of infinite two-dimensional grid. and just have a source and a source of food and a starting point. Have people thought about that sort of model at all? So where the ambient graph is infinite?
Yeah, not that I know of. So we tried to think about it at some point, and we concluded it was going to be really hard. I think Daniel, if you disagree, say. But I think, yeah, we basically thought it was going to be really hard. So our idea was to try to do some boxes, right? So you take Z2, for example, and you look at it in a box, you know, that is bigger and bigger. But we couldn't really. Could we prove something, Daniel? I think we couldn't prove something on that. So I guess my answer is it would be very interesting, but we're not sure how to treat this.
Okay, thank you.
Arjun, go ahead.
So I thought that was a really fantastic talk, and I look forward to. I think I'd like to contact you afterwards to follow up on this. But so first, I actually, in regards to Alex's question, I want to point out there's this paper that you might want to look at called Ant Nearby Treasure Search. And it's where you have ants that are in an infinite two-dimensional integer grid, and they're trying to find a point in the plane collaboratively. That's something you might look at where ants are actually in an infinite space. Okay. But for Cécile, you said you looked at superlinear reinforcement. I'm curious if you studied superlinear choice functions where they pick in proportion to the weight of the edge raised to some power that's strictly greater than 1. Perhaps that's not an interesting case, but my suspicion is you might actually see even stronger convergence if they're given anything above linear thresholds.
No, so that's the intuition at first, but in fact, if you think about it, and we looked at it on this little example, you can see in fact on this little triangle. So if you have superlinear reinforcement, unfortunately, the first few ants. So if the first few ants get it wrong, then you can in fact converge to the longer path. So unfortunately, it's a bit like, you know, I told you in these other papers about ants, even if it's self-reinforcement, the ants end up, following this cycle forever. And this cycle is random and intuitively depends on the first few ants. So somehow when you have superlinear reinforcement, if the first few ants get it wrong, then all of them get it wrong. And it doesn't work. So it's quite interesting, I think. When we started this project, we thought we would need to do superlinear reinforcement for some reason. I don't know. I mean, this was our intuition at the time, but now it's quite clear that linear reinforcement is really the right thing to do, to find the shortest path at least.
Great. Ben.
Hi, Cécile. Thanks for the very interesting talk. I just had a few sort of minor questions, I guess. So yeah, you were looking at series parallel graphs, and part of our interest in looking at random versions of those, we were interested in limit behavior as you let the number of those graphs grow to infinity with random choices. Can you treat the sort of limits as n go to infinity in that setting? Does it?
Okay, so I don't know. So our model was really like the graph was fixed, and so I don't know if you would like to look at. You can't. I mean, you can't really make the graph evolve at the same time as the ants are walking. At the same time, could you look at this model on directly on the limit? You mean some kind of? Yeah.
Does it make sense to? Maybe it just doesn't make sense.
This would be So is there a limit? In fact, can you define some kind of limit a bit like the Brownian, the continuous Brownian random tree for series parallel graphs?
Well, I mean, it's very much dependent on the bias is what you end up with. So we were interested in functions, so various random variables which should appear in the limit.
I see.
So things like first passage percolation or variables like that I just. Yeah, so that made me wonder whether is it possible to have different weights so that the edges are, have a different, there's a sort of random environment going on as well. So instead of just weight 1, they have different weights, and as you reinforce them, those,
So I think you can see that. I mean, I think we thought about doing some length indeed. So you put some kind of length on the edges, and then the ant not only, So when the ant chooses the next transition, it does it proportionally to the weights, but also inversely proportionally to the length. And we believe that this would behave the same. Well, we just didn't do it, but I think, yeah, because it's going to be more complicated, but it should behave the same. So I think on your models of graphs, if you give me any finite graph, even if it's random somehow, it should work. The question is then, if you have some kind of scaling limit, can you define the model directly on the scaling limit? We really haven't tried that. But it would be great, obviously. Yeah, let's add this to the open problems list.
And what if you have ants, you sort of have them all going sequentially, but what if you send them out as packets? When they get back to the origin, a new one starts, so you have more and more ants.
Yeah, so this is a bit what, at least intuitively for me, this is what people have already done in these mean field models, where they really see that as a flow. And it's a bit, they can also show, so in the biology literature, they did conjecture all the things that we showed. So in fact, they conjectured that the trace reinforced model doesn't find shortest path, and they conjectured that the loop erased one does. And all this doing some kind of mean field flow methods. So I guess this is, I'm not sure how, from a probabilist point of view, I'm not sure how you would send them by pack, but from a mean field model point of view, this is what people do somehow. And then they just look at an OD, right, a flow on the graph.
Okay.
I guess I have a question, suggested both by Alex and Ben's questions actually. So Alex's question, of course, is asking if you have any graph of which the random walk is recurrent, then everything still makes sense. And Z squared is just an example. I presume there's a version makes sense on any graph, or maybe trees on which the random walk is transient, because at least the first model makes sense. You have the source and know the infinity is where the food is somehow, and the trace makes sense. And I suppose at least in a tree, the sort of loop erase thing makes sense, because there's sort of the last time you left various things. I'm not sure, but I guess there's a kind of sense of the path that you followed to infinity. So so perhaps it makes sense in those as well. I don't know whether it's interesting.
I think the problem with the problem I see with having a tree with the food at infinity somehow is that which is the shortest path in that case? Can we define that?
Well, if it's a tree, then any path infinity, any that doesn't backtrack.
Yeah, but then so then the question would be, somehow, it would probably be interesting. It's true that so far we really were interested in knowing whether the ants find the shortest path. So when there is no shortest path, but it could still be interesting to see if the ants end up going through in all direction, or if they focus on one branch, right? Yeah. There is, in fact, so it makes me think there is a very recent paper about worms, right? So I told you about these other models, and there is a very recent paper where they do look at their model on an infinite tree. And I think it's super linear reinforcement, so they end up concentrating on one branch, I think. I think that's what they find. So clearly, it would make sense on any graph. You could imagine, even as you say, infinite graphs is not a problem. The only problem is to do calculations, right? To prove things.
It seems complicated enough on quite small finite graphs. So.
Yeah, at the same time on a tree you have, because on series parallel graph, the advantage is that you have this recursive definition. So on a tree you would also have a recursive definition. So maybe you could in fact prove something by saying a tree is a root and some subtrace.
That's why Ben's question made me think of it, because it might work not just on a tree, but also on some kind of infinite thing that's a bit tree, some kind of series parallel sense where you don't know exactly what that would mean.
Cécile, if you're willing, I'll take one further question, just because Lin Xiao has had his hand up for ages.
Sure, yeah.
Hi, Cécile.
Hi.
First, thank you for the very nice talk. So, maybe my first question is a naive question. I'm not very familiar with this literature of self-reinforcement random walk, but what if you, instead of reinforcing just the trace of your work, you really reinforce in terms of how many times you passed each edge? Is that a well-studied model?
Yeah, no. So I mean, no. I mean, so the model, I've really told you everything that has been done on this exact model, right? I mean, so these are these two papers. So no, it hasn't been done. So we did think about doing that, but unfortunately, so the thing is that in model T, trace, already we find examples in which we don't find shortest path. So I guess if you do that trick of saying, well, in fact, even, so imagine you're on the cone here, this one here, and you say, oh, and in fact, if I do that many times, instead of doing +1, I do plus many times, then it's even worse, right? So it's okay. So I guess this model would be worse than T in terms of finding shortest path, but I expect he would also converge probably to a deterministic limit, but this is all conjecture. I don't know, because we haven't looked at it because we were primarily interested in models that find shortest path. But yeah, it's a very natural variation. I mean, yeah. But we haven't.
That was just a naive suggestion, because if you imagine the ants don't have memory or something like that, then
yeah, exactly. So yeah, so from a biology point of view, our model is a bit stupid because we say that the ants can smell not the amount of pheromone, but they can distinguish. Oh, here, you know, I can smell that there has been, you know, 20 different ants that came, you know, and they can't smell. Oh, I can smell there is a lot of pheromones. They smell, you know, oh, there is a lot of pheromone, but only from 2 different ants. So this is a bit stupid in terms of ants. I agree that your model would be more natural in terms of ants, probably, even though I'm not a biologist, but it would be really bad in terms of finding shortest path.
And another question, so in order to maybe find the shortest path, so you said if we do superlinear reinforcements, then the ants risk of being trapped in a loop just because the initial random error. So then is it possible to do superlinear reinforcements, but somehow the weight decay over time, so that you forget the initial error eventually?
Yeah, but okay, yes.
But I realize that may be very difficult to study, but
maybe. So what I would be a bit scared is that it just changes the random path on which they focus. You see, so at the beginning, maybe they would all go, so in this tree, maybe at the beginning, they would mostly go through this path, which is not the shortest path. But then another ant would be like, maybe later they would go through this path, which is not the shortest path either. Maybe at some, you see, they would still make mistakes. I think superlinear reinforcement is not going to work, even if you allow some kind of evaporation. In fact, if I have 30 more seconds, I can say in the biology literature, it's interesting because they say that the evaporation is too slow, because you could wonder, in our model, we have no evaporation. So maybe it's a bad model from a biology point of view, but I say it's so slow to evaporate that the ants, I mean, basically the ants have eaten all the food by then. So it's just a fun fact. Okay. But no, but from a mathematical point of view, though, your question is completely valid, and it's and it would be interesting to prove something about it.
Okay, that are all my questions. Thank you for your answer.
I'm going to propose that because of the time, we take further questions sort of offline, if I can put it like that. So I'm going to stop the recording and suggest that we give Cécile a huge round of applause, and then anybody who wants to keep chatting can do so in the 20-minute gap that we'll now have between the 2 talks.